Okay.
Yeah, biology, chemistry. Actually, the
Mhm.
two different subjects. In India, in my school, of course, anywhere in my state or in India also, these two subjects actually are taught differently. So by the two different teachers.
Uh-huh.
But unlike our schools, you actually shared me that you have been teaching chemistry and biology. Uh,
Mhm.
as per my knowledge, I think both are actually taught in different way. And do you teach these two subjects in a different way, or do you integrate these two subjects? So, what will be your approach, in fact, when it comes to these two subjects in your class?
I teach them as separate classes, um, but there's a lot of chemistry in biology, so we talk about a lot of chemistry concepts in biology, but I teach them as two separate subjects, and I do teach them differently in how we like learn and practice the problems. Like in chemistry, it's a lot more problem based. Biology, we do a lot more projects. So they're definitely different subjects.
Mhm. So, how long have you been teaching these particular two subjects?
15 years. This is my 15th year.
That's
Yeah.
really a long time, in fact, as a teacher.
Yeah. And
Yeah.
I teach AP biology too, which is like a college level biology. And I teach anatomy and physiology, which is like health science.
Mm.
And then I have a science research class too.
Mhm. So last time when my students interacted with you, I think most of my students really enjoyed the session because the way you dealt the class, you showed very intriguing experiments in your classroom that really
Uh-huh.
attracted my students. They all actually were spellbound by the display that you showed on that day. So in order to make your teaching so attractive, and do you go for experimental based teaching or theoretical based teaching? In most of teachers in my region, they always adopt a approach, and they always try to explain each and everything theoretically rather than involving the students in experimental basis. So
Hmm.
what approach you actually adopt when it comes to teaching the chemistry? Chemistry, I know that's a hard one. You
Hmm.
cannot you cannot teach this topic in such a way that theoretical approach is not right as per my knowledge. So
Right.
experimental base, I think you have to go for experimental base. You have to show some I think some charts or maybe some videos, or maybe it is possible with using some teaching aids. So what's going to be your approach in teaching these two subjects?
I think that you definitely have to do both. So I think that the purpose of doing experiments is they're learning how to do science. I don't think that it's always to learn the science content because they don't always turn out right. So I think most of that is teaching students how to design an experiment and teaching them like how scientists do their jobs. There are some experiments that we use that always work out. Like you can do a yeast respiration experiment where if you put the yeast, if you do it in hot water, it's going to respirate more. Fish respiration, there's some experiments that are always going to work. Fertilizer, and those are used to teach the theoretical stuff, like the content. But I think most of the experimental part we use just to help them to learn how to do science. Um, and in chemistry, I think there are more experiments that you can use to teach scientific fact. Like you can use melting point of water and boiling point. We do that a lot, and it's always going to work. It's going to be pretty much at the same temperature. Let me think of another one. Oh, we do like density with metals. Those are always going to work. Doesn't matter how they design the experiment. Those are always going to turn out the same. They're pretty reliable. But I do think that the purpose of having students do experiments is not the same as teaching them science facts and content, and that's not what it's even for. There are great ways to teach, like you were listing some of those great ways to teach science fact and content knowledge, and that's what those are for. And then the experimental part is a different part of science.
Yeah.
So I think that's how I approach it.
Mhm. Yeah, Linda, actually, I'm waiting for some more participants. So if you don't mind, could you please go ahead and because this video is being recorded right now. So it is
Okay.
going to be shared with many participants, many teachers
Okay.
my region. So after I think yes, yeah. So after your presentation, I think I allow one of our participants to interact with you. So
Okay.
I just try to enable you so that you can share the
Okay.
screen. Yeah, please.
Okay. All right. So let me put it up there. So I wanted to start with the experimental stuff that I do with my students.
Mhm.
And I use a lot of templates for them. So I'll prepare the templates so they know what's expected of them and what they're supposed to, how they're supposed to design the experiment, and then they carry it out. So this is the template that I give them. I'm also teaching for a community college now.
Mhm.
And so those are college students, and this is the template I used for them last semester. So this class spends all semester doing one inquiry experiment, but for my students in high school, we would spend probably 3 or 4 days doing this. So it kind of varies depending on how long the class has. And I sometimes call these design your own, or sometimes they're called inquiry experiments. So this was kind of, these were the guidelines that I gave them for this class. They needed to design an experiment on a living thing. And this was an online class, so they were doing this in their homes. So I wanted to leave it, this is a lot more open than what I would do in my classroom. They were able to choose if they wanted to work with plants or seeds or yeast, worms, fish, other invertebrates, or other vertebrates, maybe pets even, that they have in their homes. And they needed to be able to collect quantitative data. So they needed to be making measurements, like taking mass, height, a number, circumference, some kind of measurement of their whatever they're working with. And then they also had to have a treatment and a control. So that's part of designing an experiment. We always have to have a control and then something we're comparing it to. And they needed to collect the data themselves. So then the next thing that they, and this one is one that I filled in. So this is similar to what the students would submit, but theirs would be blank. So I came up with first, I wanted them to ask 5 testable questions. So this is so they can practice asking questions that they could design experiments for. And these are 5 examples. So the first one is, does fertilizer increase plant growth? That's one they could do. Do different seeds grow differently? So they could test different types of seeds and look at their growth. How does sunlight affect plant growth? So they could grow plants in light or dark and compare the growth. What happens if I add more water to a plant? So they could compare amounts of water, or how much sunlight does a plant need to grow? So those are some examples of testable questions, and my students had a lot of different ones. And then they would pick one. So they would choose one that they wanted to test, and then they would move on to design their experiment. So the next step is to determine their purpose. And this is just one sentence explaining what the main idea is of their experiment. So I chose the fertilizer one for my example. And so the purpose would be to determine the effect of fertilizer on plant growth. So that's my purpose statement. The next thing they would do would be the hypothesis. And there are actually 2 hypotheses that they need to design or come up with. And one of them is called the null. And that one states that there's no effect, that the fertilizer or the treatment has no effect. And then the alternative hypothesis is that it does have an effect. And a lot of times this is actually taught incorrectly when they're younger. So I try to really have my students practice this a lot, that they do null alternative. That's how scientists do it. And we're actually testing the null hypothesis. So that's the sort of the true hypothesis. So for this example, the null hypothesis would be that fertilizer will not affect plant growth because it will have no effect. And then the alternative would be that it would affect plant growth. And you don't need to say that plant growth will be higher with the fertilizer or lower. You don't have to say that. You just have to say there's an effect or there's not an effect. So that's how we do hypotheses. The next thing is the variables. So then they have to actually identify their variables, and this will help them with the graphing part later. So they learned that the independent variable is what we call the treatment or the cause, and it's also the experimental group. And then you have the dependent variable, and that's the effect. So you have cause and effect. The dependent is what's being measured. And then the control group is kind of like the baseline, the normal one where you're not applying the treatment. And that's also considered like a group. And then you have constants, and those are all the variables that are kept the same in the experiment. So this is what mine would be for my example. My independent variable would be the fertilizer group. And then the dependent variable would be plant growth. And there are a lot of things I could measure with plant growth. I could do height in centimeters, but I could also measure the mass. I could measure how thick the stem is. I could measure how much root mass there is. I could measure how many fruits it produces or how many flowers. There's lots of parameters. And I try to encourage them to come up with as many dependent variables as possible to really see, like, maybe there's not an effect on height, but maybe there is on number of flowers. So we really try to get a big picture of how that fertilizer might affect the plant. But it's important that we only have one independent variable. We're only changing one thing at a time so we can really isolate what we're trying to find out. And then my control group would be the no fertilizer group. So I would have a group of plants with no fertilizer and also measure them to see if the fertilizer even did anything. If I didn't have that, I would have no idea what the fertilizer did. And then finally, I have my constants. And this is as many things as I can list that I keep the same in my experiment. So I'm going to have the same exact pot, same color, same size, same material. I'm going to have the same soil, same amount of soil, same density, same amount of water, same type of water. Where I put them, if I put them by the window, I want to make sure they all have the same access to sunlight. I don't want two rows where the back ones aren't getting enough sunlight, or I need to move them, rotate them. The type of seed needs to be the same. Even things like the size of seed, I don't want to use lots of big seeds for one and little seeds for another. Try to keep them all the same, make sure none of them look funny or something wrong with the seeds. So those are all the constants, and we try to come up with as many as we can. The more we come up with, the better the experiment is. The next step that they do is they write step by step their procedures. And these, I tell my students, these should be written so well that somebody else could grab this piece of paper and do the exact same experiment based on how well you explained it. So here are my steps, and we'll see if mine are good enough that somebody could replicate it. First, I would take 20 pots and put potting soil. Right away, I can see that I wasn't specific enough because I should have said how big the pots were and what color. I could have put more details there to make sure that somebody would do the exact same experiment. My next step is plant 4 radish seeds in each pot, 1 centimeter below the surface. I also didn't say in step 1 to put the same amount of soil in every pot. I should have said that, but at least I said 1 centimeter below the surface, so that's good. Then I have add 2 grams of fertilizer to 10 of the pots. These will be the treatment or experimental group, and label these pots, label the other 10 pots control. I could have been probably more detailed in how to apply the fertilizer too. And then I have water each pot with 20 mils of water every 3 days. So I'm making sure that I'm watering them all the same. And then measure the growth after 14 days. So I could have been much more specific in many places, but that's what we try to do with procedures. And this is just data that I made up. I didn't actually do this experiment, but also I put 4 radish seeds in each pot, and there's 10 pots. So I could have had up to 40 plants, and I only put 10 here. So that's another flaw, but this is my made up data. I'm saying that the fertilizer plants had all these measurements. The no fertilizer plants had all of these, and the averages were 8.92 and 6.3. So you can see that it was higher. We would have to run statistical analysis to see if it was significantly higher, but it's important that we're doing lots of different plants and we're not just basing it on 2, because if I based it on, like, say these 2, can you see my mouse?
Yeah.
Okay, so if I based it on these 2 plants, this one was 9.6 and this one was 9.8. So I might actually think that the no fertilizer group did better. So it's good to have lots of different replicates so we can make sure that we see an effect if it's really there. And then here is I always tell my students to take photos of their setup, especially if they're doing it at home, and kind of show the progress. So this is a pretend photo that I made. I have my experimental group, and my control group. And you can see I have my sunlight here in the middle, and I would want to make sure that they all had the same access to sunlight. So those are some examples of how we do photographs. And then we would make a graph. So here's an example graph. When we do graphs, we make sure that we label the x-axis and we label the y-axis, and then we also put a nice title that explains it. And I tell my students also, like when I'm doing this in the classroom and we are drawing a graph, I tell them, do you think somebody could walk into the room right now and know what we did in our experiment just from our graph? Did we label it well enough that they could walk in and get a pretty good picture of what we did for our experiment? So we need to make sure that our graphs are really complete, and you could just look at the graph and tell a lot from the experiment. Then the next step is the results. So for the results, we actually write out like a paragraph at least, and we talk about the graph in words, and we use words like reject or fail to reject the null. That's referred to the hypothesis. So the only thing we need to refer to is the null. This is an example of how you might write this up. The data rejected the null hypothesis. There was a difference between the treatment and the control groups. So remember, the null hypothesis said there would be no difference, no effect. The fertilized plants grew an average of 8.2 centimeters over the 2-week period, while the control group grew 6.3 centimeters over the 2-week period. Both groups had a wide range of heights, showing variation between each plant. However, overall, the fertilized plants had increased plant growth. So that's an example of results. The last step is they would write the conclusion, and that's like their main takeaway, main idea of what they learned. And also they talk about why it matters, what are the flaws, what can be done differently the next time. And then the hardest thing for students is how can we apply this to everyday life, like the applications. That's always the last skill that they learn, I guess you could say. My most advanced students can do it, but they're learning a lot of skills through this. So, you know, we have to understand that that's also a skill. So here's my example. We can see if I did all the things in the directions. The plants that were fertilized had more growth in the control group without fertilizer over the 2-week period. This study was only done in radish plants, so other types of plants should be investigated to determine if this is true for other plants. Also, only one amount of fertilizer was used for the treatment. This experiment should be replicated with varying amounts of fertilizer to determine the optimal amount. It is possible that too much fertilizer could be harmful. Farmers should use fertilizer to promote growth of their radish plants. So I did show a limitation that I only did it with radish plants. I don't know if other plants would respond the same. I should do more, like different amounts of fertilizer. Maybe if you put too much, maybe that would decrease plant growth. So we should look at different amounts. And then I also talked about the application. Farmers should use fertilizer to promote growth of their radish plants. So that's kind of the full circle of how we do an inquiry experiment. Yeah. And you can see from this that the point of this is not to learn the content. We're not really learning about photosynthesis. We're not learning about plant processes. We're just learning how to do an experiment. Yeah. So it's different from other parts of science.
Yeah, it sounds that a lot of activities actually in every experiment. I think you are involving the students in many more experiments, in many more activities. So I think this activity-based learning is really going to be helpful to them to understand the concept. I think you are doing really a great job, in fact, involving the students in every aspect that you are trying to do it. So Babuddin sir, are you there? Babuddin sir.
Yes, sir.
Sir,
yes, sir.
Would you like to interact with ma'am?
Yes, sir.
Yeah.
Thank you, sir. Thank you for this opportunity, and good morning, madam.
Good morning.
My question is, may I know the terminology which is related to the biology? The students, especially at primary levels, they are facing with the terminology, especially, for example, nutrients, absorb, such type of words. How can we explain clearly to the primary level students this type of terminology, madam?
So your examples were nutrients and what was the other one? Absorb? Were those
Yeah,
two
ma'am, yeah.
examples? Okay.
Such type of terminology,
Yeah.
how can we explain clearly to the primary level students?
That's a good question. I think that for us, many students would understand some of those things relative to themselves, like to humans. So they might be able to first understand things like nutrients or nutrient cycling by understanding like the food we eat. It has nutrients. Those are the building blocks that we use to grow. So I think maybe if they start learning about it in their own bodies, and I think it's always important to start connecting it to their own lives and what they understand. And then once they understand that piece, then they can connect it to the other parts, and think about how like those concepts can be applied to other parts of science, I guess. So I think the best way to start is kind of exploring what they know about themselves, their bodies, even nature. And I usually start, like when I'm lecturing, I don't really lecture, but when I'm teaching, I usually it's kind of a conversation and I'm talking with the students about what their prior knowledge is. And I kind of cater it to that. Like I know what I want to teach them, but I'm kind of discussing some things with them to kind of probe what do they know already and how can I connect that to what they know. They also might have some misconceptions about how our bodies work or how the world works. And so that's also why it's important to kind of probe and ask them questions and try to get to the bottom of what they know, and then help to connect it to what you're trying to teach them, I guess. Does that help?
Okay, thank you, madam. Thank you.
And actually, I'm expecting some more participants, but none of them actually turned up. Of course, this particular video is going to be useful for many of the teachers teaching here in my region. So before I actually conclude this session, I have a few questions, in fact, from my side. In order to teach photosynthesis, of course, it's a well-known topic in my region. What are the teaching aids that you would like to use, or would like to take the students out of the classroom and to show and to do some experiment when it comes to this topic of photosynthesis? So if you want to teach this topic, so what strategy you would like to adopt? Would you like to take out of the classroom, or do you show any other thing in order to teach this?
So like you said, a lot of students come in knowing a lot about photosynthesis. That's one topic that all my students know about. Yes. I think, well, I guess some of the stuff I use, they're called probes. Like the brand that I use is Vernier, and you can actually measure like carbon dioxide and oxygen. So we do a lot of experiments with those where we look at, so we could go out and get plants or soil, and we can actually measure how much CO2 they're using and how much oxygen they're producing. And so those kinds of experiments are really good for students to really see, like they know, they've drawn all the pictures, they understand what plants are doing, but to actually see the CO2 go down and the oxygen go up. And I think those are probably the most impactful. And then the other thing that I do sometimes is looking at water systems. So like lakes or rivers, and looking at the aquatic, the photosynthetic organisms in the water, like the algae. Those are super important for photosynthesis. They do most of the photosynthesis, but we don't think about them. We just think about plants. So those are some things that we do.
Yeah. So another thing, actually, periodic table. When it comes to chemistry, a periodic table is one of the main aspect that the teachers actually they actually stress the periodic table, and they also I think force the students to by heart the periodic table. Which is the best method you would suggest to learn the periodic table? So majority of the teachers, in fact, they pressurize the students to by heart it and blindly. And so what is the meaningful method where the students learn it comprehensively?
I don't have my students memorize it. I think that's a waste of time. We use it a lot. And so pretty soon, once they've used it, they have at least through like argon memorized. So like the first few rows, they pretty much know the mass number and atomic number because they're using it. And so I think that's the best way to approach it. And it's a tool that you're always going to have in front of you. You're always going to have it up on the wall, or you can so it's silly to memorize it. It's a waste of time. And so right away at the beginning of the year, we just start using it as a tool. And we have some really neat tables that have a lot more information than kind of the basic ones do. So they have things like melting point and boiling point and electronegativity. Like each little box has a whole bunch of little numbers in addition to the normal stuff. And so they're super useful for that too. So, so that's kind of how we approach it.
Yeah, definitely. And so another thing is when you take up any experiment, whether it is a biology related or chemistry related, what are the common experiments that students enjoy a lot while you are doing the experiment? Because kids, in fact, the age group between the 12 years to 15 years, I think they have a lot of curiosity regarding the concrete topics and abstract concepts like chemistry and biology. When a teacher is experimental and a teacher is innovative, I think students' innovative nature actually is going to be really, it's improved. So what are the topics that attract the students' attention mostly, and how do you make the students so lively and so enjoy the teaching, especially when it comes to the experiments?
I think for chemistry, the stuff that they always want to do is blow stuff up. So they always want explosions, and I am always worried that they're going to get hurt. So I'm always trying to stop them, but I do let them do some things. So they're always excited about that. And there are a lot of really fun experiments we can do that they learn a lot of really good chemistry that are explosive. So, and they're safe, I think, most of the time. And so those are fun. They also like, in chemistry, they like experiments where you make, they're called precipitation reactions, where you make a product, like you mix together two clear liquids and they make a solid. So those are always really fun because it's so surprising and you never know what color it's going to be in. And what else do they like? There are also clock reactions where the two substances will react and change colors. Like every minute, they'll change from one color to another over and over again. So those are really neat. And I also do a lot of engineering experiments. I try to do as many as possible. So I like to expose them to engineering problems, and then they have to develop solutions for them. One that they really like is, I call it life straws. And I give them some dirty water and they have to make a filter, like a tube with a whole bunch of different materials in it. And I give them water that it's acidic and salty and really hard to clean. And they have to try to fix all those things. And then I have another one where they make batteries out of metals and chemicals. And what's another one? Oh, that we have like a bioplastic one where they make plastics out of renewable resources. So those are probably the ones that they love the most, the engineering ones.
Okay.
And then for biology, like right now we're making fuel cells out of mud. So they're making electricity out of mud. And then we do another one where we make solar cells out of like blueberries and blackberries. So those are engineering ones, and those are the ones they really love too, because they're also doing experiments, but they're making something really cool, and they're kind of competitive. They want to make the best one, so those are the ones they really engage in. And for my science research kids, they it's kind of changed over the years, but right now they're really interested in sustainable energy, climate change. They're really they really want to do experiments that'll change the world. Like they're just really they really want to do something big. So
Yeah.
yeah, so those are the things they really like.
So, Linda, actually, I have to request you one thing. Your kids, your kids are so innovative because you are innovative. That's why your kids are also innovative. So I request you, if there is any possibility to organize a Zoom where your students can explain their experiments to my students, so that my students also can get that scientific temperament from your students. So they also try their experiments in their school. I think that would be a fantastic. I think if
That's a good idea.
utilize it. Yeah.
Could they record it? Could they record a presentation? Would that work?
Yeah, I think, is it possible to do it live Zoom classes? Yeah, both actually, both can be
Okay.
accepted, in fact. And your morning session would be our evening session. So if we organize a Zoom class, so that would be fine for us to see the live images, live video of your students' explanation regarding the experiments. And that would be handy, in fact. So many teachers back in India, I think they also try the same experiments in their classrooms. And so what do you say about it?
I think that sounds great. I think they would love it. Yeah.
Yeah.
Yeah, I think they would really love it.
Yeah, so let us plan that maybe in this month, if it is possible, and we can make it possible. And I would like to invite some science teachers also for the
Okay.
class. And so some students from other schools, so that they can see the kind of engineering that you are using in designing the objects. So yes, Linda, would you mind stopping the screen sharing?
Yes.
So that I can
Yep.
ask you one final question?
Yep.
Yeah. So Linda, actually, yes, science is always intriguing, because when you teach a science subject in such a way that it attracts the students' minds, definitely many students, 99% of the students are all become the scientists or science related careers. They choose the science related careers because science has the potential actually to attract the students' attention. So in your opinion, being a teacher for almost 15 years in teaching the chemistry and biology, how should a science teacher be in your opinion? So how are they are going to be teach in their classroom? So what are the strategies, important strategies they need to adopt? So what is your maybe some, can you throw some thoughts on it?
Yeah, I think that the science teacher should be like the lead learner in the classroom. And like I guess when I go to school every day, I just feel like I get to play all day. Like I just get to play with them and do science and sit next to them and watch them do the experiment and ask them questions. And it doesn't have to be rigid. And you don't have to yell at them for doing it wrong. You can just kind of let them explore on their own. And I think that my first priority is I want them to be able to find themselves in science, like find who they are in science and why science can matter to them in their lives, whether they're scientists or not. Like I've had kids come back to me and say, I was trying to fix my car the other day, and so I used the scientific method and I isolated what the problem was. Just things like that's what I want. I want it to be a part of their lives. I want it to be a useful part, and I want it to help them be healthier, where they can make decisions about their health and going to the doctor and asking questions from the doctor, and whatever their job is, I want them to use science in that too. So I think it's more than teaching them the content. It's more than teaching them these specific things that are in the textbook. It's teaching them about their scientific self and finding themselves in the science. And I guess another thing is a lot of students, at least here, have kind of a different view of what scientists do. They think that they're evil, or rich and want to hurt people. You know, that's kind of what we see with COVID and the vaccines. And so I think it's important for them to know, like, I'm a scientist. I know how to do science. I'm doing science with them, and I'm not an evil person. Like I'm here to help them. So they kind of like, maybe when the idea of a scientist pops into their head, maybe they don't see that evil person that they see in the movies. Maybe they actually see a real human, you know.
Exactly.
So those are some things that I think about. And if you kind of have that in mind, then everything else kind of leads from that. You know, everything you do, like, those are the priorities. So then you teach that way.
Yeah, agreed. I agreed. Sushila Magaru, do you have any question? We have very little time is left.
No, sir. No, sir.
Okay.
No, sir. Thank you, sir.
Okay. Linda, thank you so much for sparing your valuable time. In fact, I look forward to another session where your students is going to showcase some of the experiments. So definitely it's going to be helpful to my students as well as the teachers. So thank you so much for sparing your valuable time. I'm always thankful to you because you are always helpful to us. Whenever I request you, I think you will accept my request.
Yes.
So let us collaborate furthermore.
Yes, I always love doing this.
Yeah. Thank you so much, Linda.
Thank you.
See you soon.
See you
Thank you,
next
sir.
time. Thank you.
Thank you, ma'am.